In algebraic geometry, a moduli space is a geometric space whose points represent algebrogeometric objects of some fixed kind, or isomorphism classes of such objects. Such spaces frequently arise as solutions to classification problems. If one can show that a collection of interesting objects can be given the structure of a geometric space, then one can parametrize such objects by introducing coordinates on the resulting space. In this context, the term modulus is used synonymously with parameter. Moduli spaces were first understood as spaces of parameters rather than as spaces of objects. Motivation. Moduli spaces are spaces of solutions of geometric classification problems. That is, the points of a moduli space correspond to solutions of geometric problems. Here different solutions are identified if they are isomorphic. Moduli spaces can be thought of as giving a universal space of parameters for the problem. For example, consider the problem of finding all circles in the Euclidean plane up to congruence. Any circle can be described uniquely by giving 3 points, but many different sets of 3 points give the same circle. The correspondence is many to 1. However, circles are uniquely parameterized by giving their center and radius. This is 2 real parameters and 1 positive real parameter. Since we are only interested in circles up to congruence, we identify circles having different centers but the same radius. And so, the radius alone suffices to parameterize the set of interest. The moduli space is therefore the positive real numbers. Moduli spaces often carry natural geometric and topological structures as well. In the example of circles, for instance, the moduli space is not just an abstract set, but the absolute value of the difference of the radii defines a metric for determining when 2 circles are close. The geometric structure of moduli spaces locally tells us when 2 solutions of a geometric classification problem are close. But generally moduli spaces also have a complicated global structure as well. For example, consider how to describe the collection of lines in R2 which intersect the origin. We want to assign a quantity, a modulus, to each line L of this family that can uniquely identify it. For example, a positive angle θ with 0 θ less than pi radians, which will yield all lines in R2 which intersect the origin. The set of lines L just constructed is known as P1 and is called the real projective line. We can also describe the collection of lines in R2 that intersect the origin by means of a topological construction. That is, consider S1 R2 and notice that to every point SS1 that we can identify a line L in the collection if the line intersects the origin and S. Yet, this map is 2 to 1. So we want to identify S tilde minus S to yield P1 S1 tilde where the topology on this space is the quotient topology induced by the quotient map S1 P1. Thus, when we consider P1 as a moduli space of lines that intersect the origin in R2, we capture the ways in which the members of the family can modulate by continuously varying 0 θ less than pi. Basic examples. Projective space and Grassmannians. The real projective space Pn is a moduli space which parametrizes the space of lines in Rn+1 which pass through the origin. Similarly, complex projective space is the space of all complex lines in Cn+1 passing through the origin. More generally, the Grassmannian G of a vector space V over a field F is the moduli space of all k-dimensional linear subspaces of V. Chow variety. The Chow variety Chow is a projective algebraic variety which parametrizes degree D curves in P3. It is constructed as follows. Let C be a curve of degree D in P3, then consider all the lines in P3 that intersect the curve C. This is a degree D divisor DC in G, the Grassmannian of lines in P3. When C varies, by associating C to DC, we obtain a parameter space of degree d curves as a subset of the space of degree d divisors of the Grassmannian Chow-Hilbert scheme. The Hilbert scheme. Hilbert is a moduli scheme. Every closed point of Hilbert corresponds to a closed subscheme of a fixed scheme X, and every closed subscheme is represented by such a point. Definitions. There are several related notions of things we could call moduli spaces. Each of these definitions formalizes a different notion of what it means for the points of a space M to represent geometric objects. Fine moduli spaces. This is the standard concept. Heuristically, if we have a space M for which each point M corresponds to an algebrogeometric object then we can assemble these objects into a topological family U over M, carries a rank K bundle whose fiber at any point L, G is simply the linear subspace LV. M is called a base space of the family U. We say that such a family is universal if any family of algebrogeometric objects T over any base space B is the pullback of U along a unique map B. M. A fine moduli space is a space N which is the base of a universal family. More precisely, suppose that we have a functor F from schemes to sets, which assigns to a scheme B the set of all suitable families of objects with base B. A space M is a fine moduli space for the functor F if M core represents F, i.e., there is a natural isomorphism tau, F hom, where hom is the functor of points. This implies that M carries a universal family. This family is the family on M corresponding to the identity map 1M hom. Coarse moduli spaces. Fine moduli spaces are desirable, but they do not always exist and are frequently difficult to construct. So mathematicians sometimes use a weaker notion, the idea of a coarse moduli space. A space M is a coarse moduli space for the functor F if there exists a natural transformation tau. F hom and tau is universal among such natural transformations. More concretely, M is a coarse moduli space for F if any family T over a base B gives rise to a map phi T, Bm, and any two objects V and W correspond to the same point of M if and only if V and W are isomorphic. Thus, M is a space which has a point for every object that could appear in a family, and whose geometry reflects the ways objects can vary in families. Note, however, that a coarse moduli space does not necessarily carry any family of appropriate objects, let alone a universal one. In other words, a fine moduli space includes both a base space M and universal family UM, while a coarse moduli space only has the base space M. Moduli stacks. It is frequently the case that interesting geometric objects come equipped with lots of natural automorphisms. This in particular makes the existence of a fine moduli space impossible. One can still sometimes obtain a coarse moduli space. However, this approach is not ideal, as such spaces are not guaranteed to exist, are frequently singular when they do exist, and miss details about some non-trivial families of objects they classify. A more sophisticated approach is to enrich the classification by remembering the isomorphisms. More precisely, on any base B one can consider the category of families on B with only isomorphisms between families taken as morphisms. One then considers the fibered category which assigns to any space B the groupoid of families over B. The use of these categories fibered and groupoids to describe a moduli problem goes back to Grothendieck. In general they cannot be represented by schemes or even algebraic spaces, but in many cases they have a natural structure of an algebraic stack. Algebraic stacks and their use to analyze moduli problems appeared in Deligne-Mumford as a tool to prove the irreducibility of the moduli space of curves of a given genus. The language of algebraic stacks essentially provides a systematic way to view the fibered category that constitutes the moduli problem as of space, and the moduli stack of many moduli problems is better behaved than the corresponding coarse moduli space. Further examples. Moduli of curves. The moduli stack classifies families of smooth projective curves of genus G, together with their isomorphisms. When g greater than 1, this stack may be compactified by adding new boundary points which correspond to stable nodal curves. A curve is stable if it has only a finite group of automorphisms. The resulting stack is denoted. Both moduli stacks carry universal families of curves. One can also define coarse moduli spaces representing isomorphism classes of smooth or stable curves. These coarse moduli spaces were actually studied before the notion of moduli stack was invented. In fact, the idea of the moduli stack was invented by Deligne and Mumford in an attempt to prove the projectivity of the coarse moduli spaces. In recent years, it has become apparent that the stack of curves is actually the more fundamental object. Both stacks above have dimension 3 g-3, hence a stable nodal curve can be completely specified by choosing the values of 3 g-3 parameters, when g greater than 1. In lower genus, one must account for the presence of smooth families of automorphisms by subtracting their number. There is exactly one complex curve of genus 0, the Riemann sphere, and its group of isomorphisms is PGL. Hence, the dimension of is dim equals 0 minus dim equals -3. Likewise, in genus 1, there is a one-dimensional space of curves, but every such curve has a one-dimensional group of automorphisms. Hence, the stack has dimension 0. The coarse moduli spaces have dimension 3 g-3 as the stacks when g greater than 1 because the curves with genus g greater than 1 have only a finite group as its automorphism, i.e. dim equals 0. Eventually, in genus 0 the coarse moduli space has dimension 0, and in genus 1, it has dimension 1. One can also enrich the problem by considering the moduli stack of genus G nodal curves with n-marked points. Such marked curves are said to be stable if the subgroup of curve automorphisms which fix the marked points is finite. The resulting moduli stacks of smooth genus G curves with n-marked points are denoted, and have dimension 3 g-3 plus n. A case of particular interest is the moduli stack of genus 1 curves with one marked point. This is the stack of elliptic curves, and is the natural home of the much-studied modular forms, which are meromorphic sections of bundles on this stack. Moduli of varieties in higher dimensions. Moduli of algebraic varieties are more difficult to construct and study. For instance, the higher dimensional analog of the moduli space of elliptic curves discussed above is the moduli space of abelian varieties. This is the problem underlying Siegel modular form theory. See also Shimura variety. Moduli of vector bundles. Another important moduli problem is to understand the geometry of the moduli stack VECTN of rank n vector bundles on the fixed algebraic variety X. This stack has been most studied when X is one-dimensional, and especially when n equals 1. In this case, the coarse moduli space is the Picard scheme, which, like the moduli space of curves, was studied before stacks were invented. Finally, when the bundles have rank 1 and degree 0, the study of the coarse moduli space is the study of the Jacobian variety. In applications to physics, the number of moduli of vector bundles and the closely related problem of the number of moduli of principal G bundles has been found to be significant in gauge theory. Methods for constructing moduli spaces. The modern formulation of moduli problems and definition of moduli spaces in terms of the moduli functors, and spaces representing them, dates back to Grothendieck, in which he described the general framework, approaches and main problems using Teichmuller spaces in complex analytical geometry as an example. The talks in particular describe the general method of constructing moduli spaces by first rigidifying the moduli problem under consideration. More precisely, the existence of non-trivial automorphisms of the objects being classified makes it impossible to have a fine moduli space. However, it is often possible to consider a modified moduli problem of classifying the original objects together with additional data, chosen in such a way that the identity is the only automorphism respecting also the additional data. With a suitable choice of the rigidifying data, the modified moduli problem will have a moduli space T, often described as a subscheme of a suitable Hilbert scheme or QUOT scheme. The rigidifying data is moreover chosen so that it corresponds to a principal bundle with an algebraic structure group G. Thus one can move back from the rigidified problem to the original by taking quotient by the action of G, and the problem of constructing the moduli space becomes that of finding a scheme that is the quotient T, G of T by the action of G. The last problem in general does not admit a solution. However, it is addressed by the groundbreaking geometric invariant theory, developed by David Mumford in 1965, which shows that under suitable conditions the quotient indeed exists. To see how this might work, consider the problem of parametrizing smooth curves of genus G greater than 2. A smooth curve together with a complete linear system of degree d greater than 2 grams is equivalent to a closed one-dimensional subscheme of the projective space, PD-G. Consequently, the moduli space of smooth curves in linear systems may be embedded in the Hilbert scheme of a sufficiently high-dimensional projective space. This locus H in the Hilbert scheme has an action of PGL which mixes the elements of the linear system. Consequently, the moduli space of smooth curves is then recovered as the quotient of H by the projective general linear group. Another general approach is primarily associated with Michael Artin. Here the idea is to start with any object of the kind to be classified and study its deformation theory. This means first constructing infinitesimal deformations, then appealing to representability theorems to put these together into an object over a formal base. Next, an appeal to Grothendieck's formal existence theorem provides an object of the desired kind over a base which is a complete local ring. This object can be approximated via Artin's approximation theorem by an object defined over a finitely generated ring. The spectrum of this latter ring can then be viewed as giving a kind of coordinate chart on the desired moduli space. By gluing together enough of these charts, we can cover the space. But the map from I union of spectra to the moduli space will in general be many to one. We therefore define an equivalence relation on the former. Essentially, 2 points are equivalent if the objects over each are isomorphic. This gives a scheme in an equivalence relation, which is enough to define an algebraic space if not always a scheme. In physics, the term moduli space is sometimes used in physics to refer specifically to the moduli space of vacuum expectation values of a set of scalar fields, or to the moduli space of possible string backgrounds. Moduli spaces also appear in physics in cohomological field theory, where one can use Feynman path integrals to compute the intersection numbers of various algebraic moduli spaces. Geometric problems. Here different solutions are identified if they are isomorphic. Moduli spaces can be thought of as giving a universal space of parameters for the problem. For example, consider the problem of finding all circles in the Euclidean plane up to congruence. Any circle can be described uniquely by giving 3 points, but many different sets of 3 points give the same circle. The correspondence is many to one. Moduli spaces often carry natural geometric and topological structures as well. In the example of circles, for instance, the moduli space is not just an abstract set, but the absolute value of the difference of the radii defines a metric for determining when two circles are close. The geometric structure of moduli spaces locally tells us when two solutions of a geometric classification problem are close. However, circles are uniquely parameterized by giving their center and radius. This is 2 real parameters and 1 positive real parameter. Since we are only interested in circles up to congruence, we identify circles having different centers but the same radius. and so the radius alone suffices to parameterize the set of interest. The moduli space is therefore the positive real numbers. In algebraic geometry, a moduli space is a geometric space whose points represent algebrogeometric objects of some fixed kind, or isomorphism classes of such objects. Such spaces frequently arise as solutions to classification problems. If one can show that a collection of interesting objects can be given the structure of a geometric space, then one can parametrize such objects by introducing coordinates on the resulting space. In this context, the term modulus is used synonymously with parameter. Moduli spaces were first understood as spaces of parameters rather than as spaces of objects. Motivation. Moduli spaces are spaces of solutions of geometric classification problems. That is, the points of a moduli space correspond to solutions of